You actually have some. Say what he, how many times? Well, they're just asking. Somebody right there asking me. Yeah, I appreciate all that. And then we decant the barrel. Then it works out for you guys. Talk about wood ash, all of that, concentrator. You probably get a higher value.
Some similarities.
I don't have to clean it. You can.
They're scraping everything with many. Yeah, that's the biggest problem. We have the data. Studies to change policy to if people want to, or more importantly, an industrial scale. We have biomass generator. Yeah, because for soil health to improve it, then that's really what the target is ultimately. So it's all down to that. So a lot of the time I'm talking about it, just little people when they're asking questions. So they hear you spray. What if? So a lot of the time, a dot and this might be answers.
I don't want a dot that big.
Well, they say you can't side, right? Yeah. Well, any so we have folks in the environment. We have politicians involved. We have.
That's how I sort of judge.
Oh, so we do have that support. It's just that nobody's. So they don't worry about it. So it was basically crazy dog. The regulation was it just to catch up. Actually, no, that's color of that dog. Decades, right? So whatever the school is. And in fact, in some cases, it's actually. I always thought about that. So it's great. It's all like quality. I don't know. This is just something about. You know what? I'll ask you.
I went into a habitat is like people that do.
All right, everyone. Let's get started here. I'm George Brook. I've been involved with OMSPA for about a year and a half, working with the working groups in the strategic planning process. And I've been asked to facilitate this afternoon. This is my third workshop I've been facilitating. It's been fascinating, and I've been extremely impressed by the density of information in the presentations. We're hearing from Shaun Watmough here about wood ash recycling to restore forest soil health. And it's actually something I've just been peppering questions and realized, no, it's his presentation, so I think you'll answer a lot of them. So let me tell you quickly a little bit about Shaun. He is a full professor at the School of Environment at Trent University, and his research focuses on the impacts of climate change and pollution on natural ecosystems such as forests, lakes, and wetlands. His work looks at the biochemistry of trace metals in forests and wetlands and how climate change alters metal availability and mobility. He's worked extensively on issues related to acid rain and factors delaying ecological recovery from reduced sulfur and nitrogen emissions. Regionally, he has worked on issues related to calcium decline in soils and lakes and potential mitigation measures that may be implemented to improve forest health. He's been actively engaged with U-Links for over 10 years and has supervised many student projects working with community partners in both Halliburton and Muskota. So without further ado, Shaun, I'll pass it over to you.
Okay, so thank you very much. We've got to quite a few presentations. Obviously, I come from an academic background, and I get involved in quite a lot of research projects. I mean, 2 weeks ago I was in Guyana looking at some gold mines. 4 weeks ago I was at aluminium smelter in BC, kind of doing all our academic stuff. But this one is different. This project I'm going to talk about today, and actually is the one I enjoy the most. If I can go down here. It's because it really is working with community partners, and there's even at the end here I have a slide about citizen scientists. So while most of my work as an academic is typically in a silo, right? You go to university, you get grad students, you do that, and you produce some papers, and 5 people read them, and it has really little impact necessarily. Whereas if you're actually out working with community, with organisations, while it might not be as glamorous as the scientific papers, it actually has way more impact, in my opinion, because you're changing people's ideas, you're changing people's understanding, and in this case, we're trying to change policy. And of course, I'm kind of a supervisor, but really, it's the students, and that's the other fun part. It kind of keeps me young. I know I don't look young, but I do feel young because, yeah, I have the opportunity to work with students who are really engaged, they're passionate, they do all the work. You work with community groups, and so it's been a lot of fun. And I've been working with the group that I'm going to talk mostly about, which is the Friends of the Muskota watershed, for 4 or 5 years throughout COVID. We managed to keep it going, and it's been a real joy. And we're learning a lot, and we're also raising questions as well. And I know now that there's going to be one slide that I show. The rest of it will probably. There's one slide I think is going to perk your interest, and you're going to ask the question. And I won't say any more right now, but see if I'm right. Okay, let's do that. So again, thanks to all these folks. I'm just really the person here. So why are we doing this? So at a very simple level, it's because across large parts of eastern Canada, people have noticed that the lakes are getting, lakes, not forests, lakes. And one of the things that they see is that the calcium concentration in the lakes across vast regions has been going down. It's been going down steadily over the last 30 years. They're also measuring the biology, and they're noticing things like crayfish, other clams kind of disappearing, diatoms that need calcium are being replaced. You're getting invasive species like spider waterleaf. You're getting algal blooms. So they're seeing things, and there's a lot of reasons why they may be happening. But one of the things they noticed is that the calcium levels are going down. So they're kind of asking the question, is there a link here? Is there a cause that may be contributing with other things to the kind of health of our lakes? A lake water sample is really easy to measure. It's a lot less variable than a forest soil, where you need many samples, high geometric replication. You got to take into account the profile, the depth. To get the same level of precision, it costs many hundreds of times in terms of dollar value, and we don't have the same manpower to do it. So it's hard to track the same thing in the forest. I'm going to show you some data, but the one that really gets public's opinion is the lakes. So that's the issue, calcium going down in the lakes. So what we know as scientists is that what controls the calcium level in the lake is the calcium amount in the soil, the catchment. A lot of our work is done in a catchment basin of watershed. People will also call it. And we know there's a very strong link between the amount of calcium in our soils and the amount of calcium in our lakes. So therefore, perhaps we can say, well, we're seeing the calcium going down in the lakes, perhaps it's going down in the soils. So again, one of my students I had, and this is working with the Ontario Ministry of the Environment, Conservation and Parks now, then they were just the MOE. And they've done, and so they set up some, these are all maple dominated. The criteria here for these forest monitoring plots is there had to be at least 75% by basal area sugar maple. And so they were established across southern Ontario to the range of sugar maple in Ontario. And they measured, and they originally set up for acid rain, because they set up in the 80s, and there was concern in the 80s about acid rain, forest went back, and And so they did some baseline sampling in 1985, and 20 years later, I had a student go out and resample these sites. And they had some archive samples as well that we were able to analyze for quality assurance, make sure that the data are good. And what we saw is that top bar chart on the right there, is that actually the foliar calcium in sugar maples gone down in that 20 years across these sites. And in the very, very uppermost middle soil layer, the calcium levels gone down as well. So it kind of supports the argument that we saw with the lakes, that the amount of calcium going down in the lakes is linked to soils, and we're seeing evidence that, it's gone down over that period of time. So we do have that, okay, so it's going down, and why do we care? So a lot of work in Northeast, so it's not just in Ontario, right? There's stuff in Quebec, there's stuff in Vermont, New Hampshire, all throughout the range of sugar maple. And particularly in Pennsylvania, what they've been doing here is they say, well, they did some surveys looking at crown condition. And I should point out that we've done work looking at crown condition, and based on the observations of canopy, we can predict the risk of mortality. It's a good indicator, especially if you have 2 consecutive years, of what's the likelihood of a particular tree surviving for 15 years from now. So it's a good indicator of long-term health. Of course, as we all know, canopy condition can vary year to year, especially if you have insects, right? So in the long term, you can look at it. And what they tend to find is that the 5 stands on the right there that have the higher decline index tend to have, the lower decline index, tend to have higher soil calcium. So a point I'm trying to make here is that the calcium levels themselves don't actually kill trees. Right? It's just like you guys, you've all had your lunch, right? You eat anti-nutrients, right? You had your chapter, you're all good, right? If you don't have as much, if you don't get nutrition, you just feel a bit light, and then you're more prone to something else. It just weakens your immune system a bit, and then for something that comes along, then you're more likely to get that. And it's pretty much the same thing with calcium. It's involved in the kind of defense system of trees, as are other nutrients. And so if you start to affect nutrient balance, what will do, a tree will just start to grow more slowly, it will be less vigorous, and it will be more prone to things like insects or drought. So that's that way. And again, the same kind of thing here, a crown vigor. So as we talked about soil, this is again another study in Pennsylvania, across actually the northeastern United States. And so this is on the x-axis there, you've got foliar calcium concentration. And you see this large range in foliar calcium. Pretty much if you have over about 5,000-6,000 parts per million, milligrams per kilogram, the crown vigor index, so the lower the values, the better the health of the canopy. It's fairly, just noisy, nothing really changes. But straight away you get below about 5,000-6,000, all of a sudden that number goes up. It means that the health or the visual appearance of the tree starts to. So there's no link between, as calcium levels go down, the observable health of the tree tends to be less healthy. So that's just that. So when we then look at across Ontario, and we do the kind of thing, and we link the soil to the tree, so on the bottom axis there, we have the amount of calcium in the soil, and on the y-axis, the one going up, we have the foliar calcium. What you see is over a large range of soil conditions, there's really no difference in foliar calcium. It just kind of plateaus up and down. And so it's like a tree, just because you have more in the soil doesn't mean a tree will take up. A tree takes up what it needs, right? So over a large range of calcium, there's really just back and forth, individual site conditions will vary. But once you get, again, to this low value, which is the same value that was identified in that value here, which you can't actually see with that, on the y-axis, you start to see a drop. So the vast majority of stands at this time have sufficient calcium, but there are some sites that have calcium that is starting to become maybe problematic, and if we continue to basically lose calcium from soils, then the expectancy is that more and more sites are going to get, calcium limited. So I'm trying to sort it out. There's a nutrient problem. Not everywhere. In fact, most places are fine, right? It's just in certain localities where there is potentially a calcium problem. So why do we have that? Well, mainly because the glacial history. So not obviously around here it's limestone. There's a lot of calcium, right? Calcium problem around here. If you go onto the shield, which is not too far away from here, the bedrock changes, it's granite. And many of you have sites on sugar bushes on the acid acidified sites. And these minerals are just very, very slow to break down. You've got a granite countertop, it stays there forever, right? Limestone weathers. So what it means is that the natural release of these nutrients is very, very slow. And what we've got to remember here is that trees, if we're managing them, if we're taking products away, they're a crop, right? We're taking nutrients away, whether it's in the syrup, whether it's in the wood or the bark. We're taking those nutrients off site. And we really rarely actually fertilize a forest stand, right? Most stands are just left in natural regeneration, and the assumption in everything we do is that there's always going to be enough nutrients. Well, maybe or maybe not. It depends on the site. So the primary weathering matters. In some cases, there are anthropogenic impacts. So dust can add calcium and other nutrients to that, and we can fertilize. Right? So humans can add to the calcium, and while it's not commonly done here, certainly in Europe, in forest practices, there's a lot of addition of nutrients, wood ash, and other sources. Withdrawals, tree growth, logging, anything that takes it off site is going to take. So ultimately what determines the sensitivity of a stand to calcium or other nutrient depletion is if you're taking more off than you're putting on. It's a simple budget. So again, this is, so why are the calcium falling? All that basically says it's because historically it has acid rain. So acid rain basically leached the calcium from the soils. As we switched off that acid rain tap, we invoked policy to reduce that, we started to slow the amount of leaching. So that, in large part, is driving that decline in calcium, but also because our soils have become more acidic over that time, there's now less available in soils. So it's a combination of those two things that are causing our late calcium score. If we continue to extract calcium from site in timber and wood products, or even in maple products to a certain degree, we're going to drive those calcium levels a little bit lower. And this is just a model simulation for various stands. And the only reason I want to say is that if you look at the historic change for calcium, these three sites over 150 years, we estimated, about 250 kilograms per hectare have been lost. Last 20 years, from 2000 to 2020, we started to see some recovery. So it's a positive sign. And if we think about to 2100, we may see some more recovery, but we'll still never replace what we've lost. So in the next 100 years, we're not going to get back to where we were pre-industrially. So all that to set the scene for, well, if we do have a nutrient imbalance, should we do something about it? And in many parts of the world we do. In Ontario, we are not allowed to add wood ash. It's classified as a hazardous waste, and it goes under this NASM, non-aqueous, non-agricultural source material guideline, and basically it's based on the metal content of ash, or any product, but in this case, we're talking about wood ash. So while if you generate your own ash, you can add it to your woodlot, no problem, but you cannot transport it, and you cannot, what we're talking about here is you cannot use large industrial sources of ash to transport it to, fertilize your soil. Even though in Europe, if you actually harvest, in Sweden, you actually have to add a certain amount of ash to replace those nutrients. You're required to add ash. So in many countries, you do it. In Ontario and many other provinces, we're not allowed to. So really the goal of what we're trying to do here is ask some questions about ash. Is it safe? Can we use it? Does it give us some benefit? And can we change policy? All what I'm talking about here now is to answer those questions. Can we change it from a hazardous waste to a fertilizer that will allow us to put these nutrients back in the soil rather than landfill, which is where it's going right now. And the way obviously, I said there's two ways. The one on the left is going to be the most effective. We're doing some kind of white paper documents, we're working with ranges, and we're working very hard to try and change the policy. We believe, based on studies, that we can actually get the classification of wood ash changed so that it can be applied. And of course, as we're doing this, we're learning a lot of information, and so we publish papers, on the right there, to help the knowledge base and move forward in that regard. So we have kind of a two-pronged approach. So what I have is about 8-9 slides now. Mostly just one slide, and these are just a number of questions that we asked to try and get the information that we can provide within the issue environment, which will allow us to change the regulation. So, does wood ash, and by this I'm talking about the non-industrial wood ash, this is generated through Friends of Muskota, but also from industrial sources, pulp and paper mill, exceed provincial regulations? Does it exceed those CM1 or those CM2 guidelines? That's number one. How does the soil apply to sugar bushes? And most of this work has been done in sugar bushes. How does the soil respond? How does the soil water? So the water, remember we're trying to connect it to the lakes. The water that percolates through the soil, how does that change chemically once you add ash? How does the tree itself, in terms of its chemistry, how does that change when you add ash? Well, maple sap, right? If you're applying to sugar bush and your industry is based on that, if we're altering the chemistry of the ash, of the sap, then that's a problem. So how does that respond? What about treatment? If it's limited, obviously more growth. If you get more growth, then again, that may lead to higher productivity. We've done work in understory on vegetation and regeneration. Especially we're trying to favour maple regeneration over beech, because we don't want beech coming back. We're trying to get more maple. Maple tends to revert more alkaline conditions than beech. So can we, by adding ash, are we able to favour maple over beech? Another thing we'll talk about soil health is soil microbial communities. They change, right? The things that really ultimately drive the ecosystem functioning are all operating at a scale that we can't see. So are they changing? And we really talk about carbon now. We talk about carbon sinks, where a lot of money is going into this. How will we alter this carbon balance of forest? So a lot of these projects are still ongoing, but I have snippets of answers for most of these that I'm going to just share with you over the next 15 minutes. So this is, again, I'll explain this figure. So these are histograms. They're just distributions of individual samples. So what we did is we got ash, like 110 separate wood ash samples, analysed each one for a range of metals, because they're the ones that what the regulations are based on. So the one on the left there is cadmium, then we have nickel, then we have zinc, then we have lead, then we have arsenic, and then we have copper. And so what the histogram is showing is just each individual sample. So if you're looking at so it's a frequency. How many of the samples have a certain concentration? And then we have a couple of lines that come down. The green line coming down is that CM1 guideline, which the CM1 guideline is that you can still use it, but you have to do certain tests beforehand. CM2 is you can't use it. It exceeds the provincial regulation. You can't get a permit to apply it. So what we're looking at is we don't want to have the chemistry of our ash samples to fall above the red line. And you can see for the vast majority of all the samples we measured, they're far below the CM2 guideline. Some samples exceed the CM1 guidelines for Ontario, but the vast majority don't. So the take home for that is, ash chemistry is very variable, and that's because these are from individual sources. So you're burning, maple versus oak versus pine. What's your boiler temperature? All these things that come into it. So there's quite a lot of variability, And we do have some individual samples that exceed the CM1, but it's very rare that will exceed a CM2 guideline. And don't forget, when we actually apply the sample, so, you know, we don't actually add to the forest an individual sample, they get bulked. And so when we've done it on bulk samples, we never exceed the guideline, because those individual samples get diluted by the vast majority of other samples that are below it. So there are some concerns in terms of the metals. But the guidelines that we have in Ontario are very, very restrictive, more so than pretty much anywhere else in the world. So what we did, we said, okay then, what about if we looked at other places around the world? So we've got internationally, we've got Denmark, Finland, Germany, Lithuania, Sweden, or in other provinces like Alberta, British Columbia, Nova Scotia, or Quebec. And those numbers just represent the guidelines for the various metals. And there's only one example, which is cadmium in Germany, where our ash exceeded their regulation, and it was only just exceeded. So for the most part, ash is safe and would be allowed to be used almost anywhere else in the world, with that one exception. So that's where we're at right now in terms of, with the regulations. The other thing, this is just like a heat map. So what we've done is, so the concern is, we're adding the ash because we want the nutrients, but we don't want the metals. And so when you get a lot of nutrients, if you get a lot of metals at the same time, it's kind of not good. So what you're looking at is wherever there's a red or orange square, that means the element on the bottom is correlated or associated with the one on the right. So when you have high calcium, you have a high phosphorus. When you have high calcium, you have high magnesium. And what you see by and large is that the only element, trace element, that's positively correlated with the high nutrients is boron. And boron is actually an essential nutrient. Trees need boron. And there's evidence that trees, maple stones actually, can be boron deficient. So by and large, when the ash that has high nutrients has low metals. So it's not, so again, it's a good thing that for the most part, the nutrient concentration of ash is high, and what we're hoping to do is figure out why. What is it? Because if I was to take a poplar, for example, tree, and measure its chemistry, it would have probably 10 to 20 times the amount of cadmium and zinc in a maple. Just physiologically, for some reason, poplar trees accumulate a lot of zinc and cadmium. So if you're burning a lot of poplar or birch, then you're going to have a lot of those metals, but they're low in nutrients. So it's probably a function of what species are getting burned.
Or you said it's poplar tree?
Poplar, yeah. So, what about the soils in there? So, again, just to orientate with these figures here. So, on the top is the horizon, so we have the litter. So the three coming down on the left there are all the litter. So that's the freshly fallen litter. And you'll see on the leaves that start decomposing. The middle column going down is what we call the FH. That's the decomposed litter. So it's like humus, the stuff. And then the mineral is actually the soil itself. So they change by the horizon. So, and then what we have is three different sugar bushes, grub, marks and wilt sugar bushes. And we're on the top row, that's calcium, potassium, and then magnesium. And the red one is the control. The green is the 4 ton per hectare, and the blue is the 8 ton. And so again, the take home rate, if you add ash, what you do is you increase the calcium, especially, and the magnesium in the litter and the FH horizons, but you don't really see much change in the mineral soil. Most of what we apply stays in that organic resin. It takes time, and so these studies only started 2-3 years ago, and we're starting to see slowly the increase in nutrients in the mineral soil, but for the most part, the responses are restricted to the organic horizon, the litter and the FH. Potassium is something that is a little bit different. Potassium kind of shoots through the system quite quickly. Unlike calcium and magnesium that kind of get held onto the soil particles, potassium is a monovalent, very mobile ion, and it just kind of shoots through the system, which means it doesn't have a strong legacy in the soil, but as you'll see, the trees take it up very, very quickly. What about the metals? So again, it's the same thing here, except we've got the brook side is now coming down the column, and the horizons are now by the row. So we've got the litter, the FH in the middle row, and the bottom row is the mineral soil. Again, we've got the three sides. And again, we're adding ash that contains cadmium, and we measure it in the litter. Right? So we do measure an increase in cadmium, but we do not see it in the FH, and we do not see it in the mineral side, which really kind of makes sense because we know the cadmium's in the ash. And we're adding it there, but we don't think that this concentration in the litter is high enough to cause any adverse effects on. This is again, this is the soil, one we're going to show here. So what we have is we measured soil water, just pH, right? pH over 3 years, 2019, 2020, 2021, again in different horizons. So beneath the forest floor, beneath the LFH, at 30 centimetre depth and at 60 centimetre depth. And if you just look at the left one, the LFH, the control at a pH of about 4.5, whereas the ash treatments that we applied, in this case it was 2.5, 5 tons and 7 tons, went up to about 7. So the ash dissolves, it increases the pH of the water. It's very, very pronounced draining that forest floor. But just like with what we said soil, if you look at the deeper horizons, while you can see in this middle set of rows some evidence of an increase, pH is a little bit higher. It's not dramatic, it's not like the forest floor. And by the time you get to 60 centimetres, you really don't see an effect at all. So most of the effects that we see of the ash on soils are restricted to these uppermost organic horizons, and they're starting to appear in the upper mineral soil. We didn't see really any metals, so the metals were not really getting mobilized in the water. The only ones that went up were arsenic and molybdenum, but very, very tiny amounts. They're well below any water quality guidelines, and actually most metals went down because the pH, the higher pH, metals are less mobile, so they don't get released. So again, there's no real strong evidence that the metals are increasing to higher levels of concern. Trees. So again, now we've got mature trees, saplings. Again, these three sides. We've got calcium on top left, magnesium, we've got potassium, and we've got phosphorus. Just like before, the red is the control, the 4 ton is the green, and the 8 ton is the blue. And you can see that calcium at the three sides is starting to go up 2 years after the treatment. But if you look to the right, the potassium is kind of almost doubled. So potassium concentrations, once you add the ash, the trees suck it up. They go up, phosphorus has gone up by about 50% at all three sites after 2 years. Magnesium has gone up by about, again, almost doubled in both mature trees and in saplings. So again, we see a very, very strong response in the trees, both mature maples and sapling maples. We measured metals. Some metals increased very, very slightly by about 10%, but again, I could go to other sites and measure those concentrations occurring naturally. So nothing above what I have not measured just in a natural forest stand. So the trees respond positively. So the soil responded positively, the trees responded positively. Well, it's sap. Well, the reason we did this, we did it over 2 growing seasons, and it was to, again, it's all about the chemistry. We added these chemicals, or ash that contains chemicals, onto a forest soil, and it goes into the sap. That was a general problem, but we also measured flow. Right? And in 2021, the sap flow was double what it was in the untreated stand. So, so we had 12, I think we had 12 trees, that we treated and 12 trees that we didn't treat. So the treated trees are the blue line, and so we applied in the fall, and then we measured it through that tapping season, and then the following tapping season. First tapping season we got double the full, second season was back to zealous. We measured the sugar content, the pH, all the nutrients as well, and all the data are here. There's nothing untoward, there's no difference. So there's no dilution effect, for example, with that increased flow. The concentrations and everything else we measured, just if we allow for the concentration factor, taking account the sugar, the amount of concentration you need to get to syrup, all the values are within the range of what you'd see in the published literature. So there's no evidence that adding the ash to a sugar stand alters the chemistry of sap in any way outside of what occurs normally. And then again, I'll skip this one because these are again just showing the same thing with the nutrients. Tree growth. So one thing we've been doing is that you can go and you can measure tree growth just with calipers. If we all went out and measured the same tree, we'd probably get a different number because it's a bit subjective where you're doing it. So what we've done is we put these things called dendrometers, band dendrometers, that you strap to the trunk of a tree, and it measures at the same spot continuously. So it's a very, very accurate way. So we've only just started doing this, and this just shows how you can measure. We have, I think, 12 trees for each treatment. We're going from 0 from a control, 2 tons, 4 tons, 6 tons, and 12 tons, just to see ultimately what the effects are. It's only just started, so really the control is right in the middle there. I think the highest was 4 tons, the lowest was 6 tons. There's no relationship at all with treatment in the first year. So there's no evidence right now that we're seeing it, but we didn't expect that. We didn't expect it to occur in a year. We did a study in Alabama Forest where we looked at 4.5 or 4.25 years where we added ash. So and the only thing I want to tell you is when we added 8 tons of fly ash, in terms of it was separated by maples with a diameter less than 24 and greater than 24. And in both cases, after 4.5 years, trees receiving the highest dose of ash, fly ash, showed positive growth response. We've done meta-analysis that similarly shows that the response to tree growth is a lot longer than the chemistry. The chemistry responds immediately. The time it takes for trees is longer. So we don't know where we're at. We're going to start the tree growth. The idea is to keep those going for 3 or 4 or 5 more years. And we should have a lot more better or more accurate understanding of what the benefits are in terms of tree growth. Soil microbial communities, really not much happened. There was no effect on soil eukaryotes, so soil fungi. We looked at mycorrhizae, we looked at a whole suite of things using RNA and DNA techniques. We didn't see any difference at all with treatments with eukaryote. The only thing we saw was with bacteria, soil bacteria, prokaryotes, only at the highest treatment. In this case, it was 7.5 tons. So this was 3 years after we applied the ash. We went and we looked at the soil, and again we measured the bitter, the FH, the AH, which is that mineral soil again, right? And only in that FH horizon, which is where the chemical change was the greatest, where the pH was highest, where the nutrients, we saw more diversity. There's a greater diversity in soil bacteria, and if you look, that's driven by that green blob there. That's the group of bacteria that like acid conditions. So what you've done is by adding sort of an alkaline system, those bacteria that don't like the acid conditions have diminished, and you've allowed other types of bacteria to exist in the soil. So that is the only effect that we observed after 3 years on soil microbial communities, an increase in diversity at the highest treatment, and it was the acid-loving bacteria that kind of went down, and some of the other saprophytic type of bacteria that increased. soil respiration. So when you add, so the other line is actually that's not necessarily a good thing for the climate because you're going to release carbon dioxide to the atmosphere, so it's not going to happen. Wood ash adds calcium carbonate, but it also has other forms of calcium, calcium hydroxide and calcium oxides. So when you actually add ash to a soil, the first thing you see is what happens in the green there. The soil sucks up a lot of carbon dioxide. And the reason it does that is because the calcium oxides and the calcium hydroxides in the ash are weathering very, very quickly and it's creating calcium carbonate. And the way it creates calcium carbonate is by reacting with CO2 in the atmosphere. So it actually, for a short period of time, it's a carbon sink. Well then, after that, what you see is, over the rest of the year, there was more respiration. And what we're working on now is we're determining, is that because we've changed more favorable bacterial conditions and there's more respiration? We know pH is something that soil microbes really react to. And if we've increased the pH, if we've increased the quality of the soil, we may get more microbial activity. Is that what's going on? Or is it just simply that calcium carbonate being weathered again and releasing carbon dioxide just like limestone would? So again, so that the effect of wood ash on the carbon wood is kind of mixed. Initially, it's a sink, but after that, it looks like that CO2 is going back to the atmosphere. And the last thing is citizen science. So what I've talked about is a lot of studies, a lot of questions about the science. But all these projects are done based on grant money and proposals. They're done on a student project. And something I've said here, we don't have the answers to. We've not got enough time. Some things take a longer time to respond than a master's project, for example, or even a PhD project. And so what we've done is, again, because we know that the community is really actively engaged, we said, well, there's a lot of interest by the public. What about if we get them to do the work, or get them to do the measurements, and just start to collect data over a longer period of time that goes beyond the period of a study to allow us to answer these questions that right now we can't really answer because we didn't have enough time. So that was what it was. But the real problem there is, what about the quality of data? If we get people to do these measurements, are they going to do it well enough for us to reliably use it? So Kira Aker, she did a study with folks in Muskota, where she basically put together a pamphlet, and we just chose a few parameters: tree height, tree diameter, there was tree species, canopy condition, and she basically gave them a pamphlet like this. I told them how to do it. They went out and did it, and then she went out after them and did the same measurements, doing it as a trained person to see if they got the same numbers, right? Just complete, so it's complete abandonment, do citizen science data, so this is what she found, which is quite interesting. So what I've done is on the bottom axis, that's Kira's data, so that's someone who's been trained, and we assume those data are reliable because she's doing it using the data. And on the y-axis is the citizen science. So these are data provided by the citizen scientists. So the top left one there, so what that is, that's soil pH. And so it's not, so because it varies by depth, if you take a sample of soil and you capture that up a centimetre, whereas if you sample that much, you're going to get a different pH. And we told them a certain depth. So we're using pH as a way of seeing how accurately people can measure soil. And if it was perfect, it was absolutely perfect, everything would fall along that green line. The number obtained by Kira would be exactly the same. Now, in reality, even if Kira went back and did the same thing again, for soils you wouldn't get exactly the same number because you can't sample the same soil. You can only sample something right near it, next to it, and that will likely be different anyway. So what you don't expect the same number, but you expect a relationship. And what you can see here is that, yeah, there's a relationship, right? So as the values go up in by Keeler's data, they also go up by us in science, but it's very, very noisy. So, yeah, there's probably some problems with soil sampling. It's generally okay, but it's not really accurate. If you go down, look at tree diameter, again, a lot of the numbers fall right on that line. It kind of makes sense. Tree diameter, where you give people away there, it can be done fairly accurately, right? You get a few outliers, and actually, these two here, anybody any idea why those two numbers are going to be so far out?
Is there a branch note or something right there?
No, it's because inches versus centimeters. Again, it's an interesting thing about communication. A lot of folks use the old imperial system in inches, and we're working in centimeters. And so it's just, when we convert them from inches, it actually falls right on the line again. So again, it's a lesson learned, right? Make sure you don't assume anything. Make sure that you make your instructions very clear so that, so it was good, I think, for tree diameter. Tree height, which is the top right one there, also pretty good. Obviously, the smaller tree, the one left, more accurate. As you get taller and taller trees, then you start to get more and more scatter. So, yeah, but overall, I'd say it's reasonably good. Like, the one that was terrible was canopy condition. So this is looking at how transparent a canopy was. And you see for that we didn't see a relationship at all. And so the question is, why? I mean, was it that the instructions weren't clear enough? Or it's just more subjective anyway? And it's a harder parameter to measure than something much more physical. So ultimately, I think citizen scientists promise, but it depends on what we ask them to measure and how accurately we can give them the information so that we can get reliable information. But what this will allow us to do is, again, if we're thinking about tree growth, something like that for the future, a project may end, but we have engaged in, we're using their property, perhaps they can monitor that for 3, 4, 5 years afterwards, and at that point, we might start to see what the longer term responses are.
Shaun.
Yeah, this is it. So, to conclude, really, wood ashes, rich in nutrients, and by and large, metals don't exceed the frictional guides. When we add it, it does increase the soil base status, soil pH. We do see some small increase in metals, but only in that organic horizon. The trees respond rapidly to these nutrients. They increase in the foliage, both saplings, mature trees. We didn't see any adverse effect on sap chemistry. In fact, we saw increased sap flow immediately after doing that. The short-term response to growth, we don't see anything yet. Indications are that this will take 4, 5, maybe 10 years to materialize. I'm not showing this for time. Understory community diversities are a little bit different, again, because we're changing the pH from 5 to 7, but not vastly so. Again, small increase in microbial diversity, and the carbon fluxes are somewhat mixed. So we're getting a lot of information. We've not answered everything, and we're working on some other things. We're planning to try and do it at a catchment scale now. So we've done all the work so far has just been on small plots. But now we're hoping to actually do it on a 20-hectare catchment where we can actually bring in, birds, amphibians, and snails, and more ecosystem processes as well. Yeah.
How deep is the ash that you were adding?
So when you add it, we go right at the beginning.
Oh, I missed the first.
No, right at the beginning. That's what it looks like. Immediately when you add it, so it's like a covering. It's just a covering. So I know 4 tons, 8 tons sounds like a lot, but it's just like a covering. And actually, you apply in the fall, and you come back in the spring, you can kind of still see it though. It kind of stays visible for a year, and then kind of the fresh leaves come on and it starts to get better, and slowly works its way. Anyway, that's it.
And how many times a year do you think, or just, you added it just once a year? Or?
Yeah, so the intent of this, the dosages that we're using are all based on what we believe has been lost from soils since the inactivity is started. So what we're trying to do is replace the calcium, magnesium, potassium that's been lost through harvest into acid rain, and we estimate it's about 4 tons of ash equates to that much nutrients. So that's where it comes from. So it's meant to be just a one-off application. If you are harvesting, then the idea would be you would apply it to replace what you're taking away from in the wood. Yeah.
How many tons of calcium per acre would that work out to on your 2 sites?
So by weight, calcium is about 30% of ash. So yeah, that's the best way to do it.
So like 2.5 on the one in one shot?
Yeah.
And you didn't see any damage to the trees, like any shock or anything?
No. Yeah.
I think it was the very last slide. One of the last points you said the understory, the under canopy community.
Yeah, so we're measuring.
Affected, but you didn't say negatively or positively.
It was like so we had 3 stands that we were measuring it. 2 stands didn't change. 1 stand had slightly more diversity. But it isn't affected now, but we're still going. We didn't see any real change in community composition. So, we didn't lose any species that, we saw. Just a relative abundance of ones. And we now got 3 years of data. And there's not been, that was only one significant response, which we all the metrics as well. So I had 3 stands, 1 stand that's slightly higher at the highest rate. Yeah.
A source for wood ash, a large source to put this much on land, where would this eventually come from, or just?
So in Northern Ontario, the burning wood, have been refurbished to burn wood. The pulp and paper mills, they have a lot of ash as well. So those are the 2 major sources, but scale.
Did they sell it or give it away?
Oh, we give it away, because right now they have to pay the tipping fees for landfill.
But not accessible yet.
You're not allowed to do it, that's why they have to landfill it, because they're not allowed to put it onto the forest. Yeah.
Have you found that the pulp and paper wood ash is higher in the metals?
Not noticeably so. So of all the surveys, the stuff from the non-industrial, which is mainly hardwood, by far one of the lowest in general. But the pulp and paper, because they burn a lot of, you get a lot, but not noticeably so. So it didn't exceed the regulations.
So everyone, I'm just conscious that we're at the far campus and there's another workshop, so we're not going to shut down the questions and answers, but I wanted to give people, if they have to go to the next one, a chance to quietly just get up and leave. So that being said, I just have one reminder from the organizers: please fill out the evaluation and hand it in. And a huge round of applause for Shaun. And again, I invite you to stay and continue the questions, but if you have to leave.
I have a question.
Yeah.
Would I be safe to think that burning dead beech and dead anything and spreading them in ashes could only enrich my earth?
Yeah, exactly. I mean, it's actually most farmers are anecdotally and actually that improves, right? So, good one, exactly. It is a fertilizer. It is in the earth as a fertilizer, but not in Ontario.
Me?
Yeah.
Yeah, well, kind of. So we have an outdoor wood stove, and we just throw that into our apple orchard.
Yeah.
And it seems to actually be really beneficial for it. Does it matter? Like, because it's like cedar and it's like ironwood, it's all mixed.
Exactly. So most of the ash we deal with is mixed sauce. So it's actually fine, right? So, and as you say, you do it. So we know from anecdotal that it benefits, right? And so that's the irony that we're not actually allowed to do it at scale. So all this work is trying to allow us to scale up so that rather than going to landfill, we can actually apply it more widely. Yeah.
Is there a level of wood that becomes toxic?
Well, that's why we're doing these things up to 12 tons. We're trying to look at that. We've not seen any evidence. And in the literature, they need stuff up to 90 no one's ever going to be finding 90 tons per hectare bag. So we've got as far as 12.
What does that look like on the ground? How deep?
Okay, 12 tons is like you don't see the leaves. Right, so that first picture you saw, you can still see the foliage. It's like a thin dusting. When you like, that was 4 tons, that one. So triple that amount. What it would look like. Quite a lot. And it's also logistically how you get out of there as well.
What about agricultural lime?
Yeah.
I was getting kind of a negative impression from putting lime on it, from what you were saying.
Well, it's no lime, it's done, but the thing about lime is, it's really just calcium, pH, so it doesn't contain phosphorus, boron, all the other nutrients as well. If you think about it, ash is all the nutrients that were in the tree that were taken up in the proportion that the tree needs. So if we put it back on, we've got a balanced fertilizer. The only thing that's missing is nitrogen, because nitrogen is volatile and goes up when you burn it, right? But right now, atmospheric deposition of nitrogen is elevated 10 times above background anyway. So, our activities inadvertently are adding nitrogen to our system anyway. So you've got a balanced nutrition source if you use ash, whereas if you want to increase pH, then it's fine, but the carbon footprint of lime is bigger, because you're mining it, you're transporting it, and you're adding calcium carbonate, which is going out, whereas with ash you do so it's got a bigger carbon footprint. Yeah.
I'm fairly new to this, and I don't know if this is a question more for the membership or for yourself, but you're saying like this is to offset what we are depleting, right, from the ground. So in terms of windfall, down trees, and that, how much is that contributing? Like, what's the standard practice, or how much does it contribute to enriching the soil versus, ash? Like, is there a certain amount you should leave as adding back to your soil? I don't know. You know what I mean?
No, I know what you're saying. I mean, so in a natural system, that's what happens, right?
Yeah.
Trees will die, and it's a tight cycle. And so what we do is when we're managing forests, we do take something.
Right.
And we don't necessarily think about adding nutrients back, because we believe and for many stands that's fine, because compared to other crops we won't take the same intensity of nutrients away. So it is sustainable.
Yeah. So how much should you leave as just
Well,
back into
what you can do is you can do soil tests, and what that will allow you to do is work out the carrying capacity, and that will vary depending on your site condition. So richer sites you can take more, poorer sites you can't take as much. So it will all be based on the condition of the soil, and you can take some tests and then do an analysis to work out what is the allowable cut that you can take.
Okay. I was just curious about that. Okay, thank you.
You know what the soil pH was to start? Like, so for us, we're 2 hours east of Sudbury, and our soil pH is pretty bad, so we spread agricultural lime and sugar bush to raise it.
Yeah.
And I believe we were told to keep it around a half a ton an acre, so we wouldn't shock it.
Yeah.
Because of the difference that we were looking for.
Yeah.
I'm just curious, like.
So these soils, the mineral soil would be about 4.
Okay.
So probably similar to yours, I imagine. Your soil.
Yeah, I remember that presentation. I don't think it was you. There was another fellow previously that was working with Brooklyn Farms in Bracebridge.
Yeah.
That was involved as well.
Yeah. So yeah, it's like pH 4. I mean, most of the shield sides it's fairly homogeneous, right? I mean, you can get slightly richer sides, but most soils have a pH between 3.5 and 4.5, unless you're in a little outcrop somewhere different.
And it is like conclusively linked to crown dieback now, or?
Is it linked to, I mean, it's like everything else, right? There's associations. When you have low, you see, visible, but there's always a lot of noise, right? It's never something that you can, on balance, I'd say all it does is it makes the tree weaker, and something else is what's responsible for the dieback. So whether you've got, drought, you've got poor, shallow soil, most sensitive to drought, or whether it's, for example, in Pennsylvania, what they were finding was after a defoliation event for insects, trees that had higher calcium were able to get a second flush. The trees that didn't die, didn't have enough resources to actually recover from that defoliation event. So it's kind of things like that that matter. You know, but I've seen trees with really low calcium hanging on there, and they just grow really, really slowly. Just hanging on, so.
I have one last maple related question. So when we take our sugar sand out of our syrup, it's calcium malate. It's the malic acid and the calcium precipitating when we boil it and we throw it back in the sugar bush. But it's not very soluble. What are your thoughts on that and slow leaching of calcium?
Yeah, I mean, you're right. I mean, there are lots of different I've actually got a student working on various species of calcium in soil, right? It will release, right? But it'll be very slow. I mean, you're putting it into a soil, the water that percolates through that is a pH of about 4. So it will slowly dissolve. So, you know, I wouldn't worry about it. I think it's better to use that than do it somewhere else, right?
Well, yeah, it's calcium we take out every year.
Yeah, exactly, right? So I would definitely do what you're doing. It makes sense.
Yeah. I guess my last thing is we have a furnace too, and we've just been piling it in a pile. Is it still viable, or have I lost most of that to leaching? Like, if it's a visible pile, is that still mostly calcium, or?
Yeah, it'll be the calcium will be there. What has probably happened is weathered, so it's more calcium. So the pH will be lower. So I'm sure that if you get fresh ash, the pH, you know, particularly the high ones is about 12. It's really high. If you leave it, our pH will drop to about 9. And what's happening there is that the calcium oxide and hydroxide over the atmosphere are converting to calcium carbonate, which has a low pH. So that's what's going on. So it's the same amount of calcium, it's just in a different form.
Okay. So it's still good to go.
Still good to go. Yeah, it's still good.
Perfect. I know where that's going.
And you're not going to have any slugs with that diatomaceous earth you're putting on.
Yeah, I do think about the silica dust, but that's okay. 1 year leaf litter makes it disappear. Yeah, really, we only take it for like 5